Let's begin. It's an honor to introduce our first Gilbreth lecturer, Mr. Bo Naasz. Bo is a senior technical engineer at NASA, where he currently leads NASA's agency-level rendezvous and capture system capability leadership team. While his most recent duties are directed towards agency-level strategy, mission systems engineering, and project management, his background is in spacecraft guidance, navigation, and control. Bo was the flight dynamics lead for the Hubble robotic servicing and Gilbreth mission in early 2000s, and later the principal investigator for the relative navigation system experiment on Hubble servicing mission 4. Today, Bo will walk us through the design of space systems to enable in-space assembly and servicing. Please join me in welcoming Bo Naasz. Bo.
All right, I got a water here. All right, well, thank you, NAE, for having me here. Such an honor, and I'm in awe of the brain power in this room. Congratulations to all of us for being here. So I work for NASA, so that means I have to have 7 acronyms in my title. There's a laser pointer, great. So I'm the ISAM and RPOC system capability lead. So ISAM is kind of going to be the main focus of our conversation today. In-space servicing, assembly, I almost forgot my own title. In-space servicing, assembly, and manufacturing. So these are operations in space. So let's talk about exactly what that means. So most spacecraft missions have a pretty linear, simple flow. We study and develop and fabricate and test, and we spend sometimes decades doing that for a spacecraft. We launch a spacecraft over the course of a few hours, a week-long campaign. We check it out and make sure it's working, and then we operate it for as long as we can before something fails on it. And usually, we design our spacecraft to operate for a minimum of 5 years, but they often operate for 25 years or more. And often, the thing that it results in us finally turning them off is that they run out of fuel. So we're talking about multi-billion-dollar spacecraft, and a lot of times at the end of their life, they run out of fuel, so we turn them off. So, and then, of course, we decommission them. So my kind of role is to try and think of another way to be a little bit more flexible and maybe a little bit more sustainable. And so we'll talk about those options to do that. So we have servicing. Servicing of the boxes in green here. If we incorporate some multiple launch and some rendezvous proc stops and capture, I'm sorry about all the acronyms, but you'll get used to it if you're an engineer. Robotics, so if we enable those things, then we can do some interesting things in end of life. We can use spacecraft to go up and dock and relocate. We can refuel them. We can inspect them and figure out what's wrong with them. We can remove or dispose of them, which is a pretty interesting topic these days as we talk about the orbital debris environment. So we add some more cross-cutting thinking, these gray boxes. So if we actually plan from the start to design in the ability to service spacecraft, and we plan from the start to plan for multiple launches, then we add some really interesting new things that we can do. We can fuel, so launch tanks empty, and get more on orbit. We can use robotics to aid deployments more reliable, and we'll talk a little bit more about that later when we bring up James Webb. We can upgrade, maintain, replace, and repair. So, you wouldn't buy a computer if you couldn't, well, actually, holy smokes, I just dated myself. I was going to say you wouldn't buy a computer if you couldn't take out a component and put a new one in, but actually you really can't do that anymore, can you? Okay, and so then if you can bring things back, so you go launch a second time and catch it and bring it back, you can refurbish it and refly it, and we actually do that. I'll talk about a couple of missions that we do that on, not very many of them. Next, we add assembly, so you can assemble things in orbit. I won't get into too much detail there, but maybe the most interesting is assemble huge precision apertures, and we'll come back to that idea a little bit later. And now you can also do manufacturing in space. So if you have materials in space, you can manufacture large infrastructure, use that to assemble things in space and operate vehicles. You can manufacture goods in space for Earth use, and there's a lot of people working that. You can manufacture parts and use them for replacement in space. And you can recycle, maybe use material that's already up there to build new things in space. And a lot of interest in that for things like Mars exploration, where humans might be gone for several years. They can't take all their spare parts with them. They just can't afford the mass, and so maybe they produce them on the way when they need them. So a lot of interest there, and I think we're going to hear some more about additive manufacturing later. We're counting on you. Interoperability is just something, you add standards in the beginning. That means everybody can use the same things. So there's a lot of talk about interoperability, especially on the lunar surface. As we go back to the moon, we want to be able to stay there, and maybe we want to make sure the things that land there have interchangeable parts in case one's batteries die. You can take one batteries out and plug them in the other. It seems like a no-brainer, right? But we don't do that in space yet. And then another really interesting kind of parallel activity that I don't lead, but I'm very interested in, is in situ resource utilization. This is mining regolith on the moon or other planets, asteroids, comets. We can generate fuel, hydrogen, oxygen from water. And of course, we also probably will need to maintain those systems. They're going to be similar to big tractors and construction equipment, and mean time to failure on those things is, I'm told, well, they operate them something like 20 hours a day. I'm making that number up. And then they have preventative maintenance 4 hours a day on those things. So they're repairing them every day on those large mining equipment. We obviously do not do that on the moon right now. We don't do anything on the moon right now, so. Okay, so that's what servicing, assembly, and manufacturing is. So let's talk a little bit about why. So everybody knows about Hubble, right? Well, so this is the first picture, or the early pictures of Hubble after it launched. Servicing mission 1 put a corrective optic in, made it look like that. So we all know that Hubble was saved by servicing, okay? Maybe what we don't realize, so here, this is that camera that took that picture. So this is servicing mission 1, astronaut installed, astronaut Jeffrey Hoffman installed that instrument in Hubble. Okay, so and took that great picture, and lots of great pictures after that. That's the wide field planetary camera. Okay, so we know that it was saved in the first mission. What a lot of us probably don't know is that we went back to Hubble several times, and the reason Hubble is such a remarkable machine is that we went back to it 5 times. We replaced a lot of equipment on Hubble, but most importantly, we put new instruments on Hubble. So the instruments are where the magic is. That's why we fly it. The optics, a 2.4 meter mirror, that technology doesn't change very fast, but cameras change very fast. And so every time we went back, we put a new instrument on. You can see I'm an engineer, I had to put a plot in. So this is a way of understanding how much impact Hubble has had. So this is science metrics. It's a unit that we can talk about later if you want offline, but I won't get into it. It's a measure of how productive a mission is. These are several NASA missions, and you can see Hubble, this black line, going up. And of course, every time it peaked was after a new instrument was installed. So if you think about this, over the life of Hubble, I think $16 billion was the cost of the life of Hubble. About 10 billion of that for the launch, so the 10 billion gets us to here, okay? And then 6 billion gets us to here. All right, so that's the value of servicing. It's very clear for exquisite national assets that upgrading them is a good thing. Okay, so what came after Hubble? Y'all have seen the James Webb pictures, and these are phenomenal pictures. And this is a extremely challenging mission. I can't tell you how hard this mission is. They had to fit this large segmented mirror telescope into a launch vehicle. Launch vehicle fairings are 5 meters, the bigger ones now. We've got some bigger ones coming, but they had to pack this thing into a really compact space, get it out 1 million miles from Earth, and operate it out there. Once we launched it, nobody was ever going to see or touch it again, okay? Which is true for most spacecraft, actually. Hubble's kind of an anomaly. So as this movie plays, you'll see something like 150 mechanisms deploying, every single one of them a single point failure, meaning if it didn't work, the mission was over. The mission was failed. As a servicing guy, well, I'll tell you, almost all engineers that watched this were extremely nervous. But as a servicing guy, I was super nervous because I knew that if those things didn't work, I was going to get a call. And frankly, I didn't know how to fix that telescope. It wasn't built to be fixed. But of course, we would try something, right? So I didn't get a call, as you all know. And Webb has just been producing some awesome pictures. So why assemble? So we talked about why servicing on Hubble was great. So why should we assemble? Of course, it's for big science, right? These kind of things need to be big. You can't launch them. This is actually a concept called LUVOIR. That's the biggest deployable telescope we could possibly launch. It would fit in an SLS, 8-meter fairing, I think. Lots of folds similar to James Webb. But so this concept is intended to answer the question, are we alone? And NASA has recently just announced that they're going to call this next thing. It won't look like this. It'll be closer to this size. But they're going to call it the Habitable Worlds Observatory. And the point of that spacecraft will be to do spectroscopy on the reflected light of planets, extrasolar planets around stars. So I have another plot here for you. This is exo-Earth candidate yield. This is the number of planets that we think we could find and image, do spectroscopy on. And spectroscopy means figure out what gases are in the atmosphere of that extrasolar planet. So if we see there are certain lines in the spectrum that we only see emanating from Earth. They're the lifelines in the spectrum. And if we see those spectra, it's an indication that there might be life on that planet. So the number of candidate planets we can look at is a function of how far away they are, how many stars there are nearby. And the number we can see it has this relationship with the diameter of that primary mirror. So if you look here, this is James Webb. Hubble's down here. Sorry, this is James Webb. The Habitable Worlds Observatory will probably be in this range, which means we're going to have the opportunity to see something like 30. So that's not very many. But we're going to look at 30 stars and look at their planets that are in the habitable zone where there might be life, and we'll look at the spectroscopy from them. As we get bigger and bigger, we can do more and more, right? So bigger is better for finding life in the galaxy. So that's why we would assemble. So that's where we go to something like this. So the biggest we could possibly deploy, and then there's concepts like this one. This is a 20-meter assembled telescope called ISAT. Very challenging to launch this. Probably something like 10 or 12 launches in that 5-meter fairing. Okay, so why else servicing and assembly? Human exploration. Human exploration is the poster child for servicing and assembly. We built Space Station. I did the count this morning. I think there was 200, I got it right here, 263 launches, 111 of them crewed, to build and maintain and operate the space station. So awesome ongoing international project. Of course, we're doing Artemis now. You may have seen Artemis 1 just went uncrewed around the moon. Artemis 2 will go crewed around the moon in 24, and then Artemis 3 will rendezvous with Starship in the NRHO orbit around the moon, in cislunar space around the moon. This Artemis rocket is based on the Starship vehicle that I don't know if anybody's heard yet today. They were supposed to do their first hot fire of 33 engines. This is a game changer, 100 metric tons to low Earth orbit. To get it to the moon, they have to refuel in low Earth orbit, and it takes something like 12 launches of that behemoth rocket. The first one goes up as a tanker. The next 10 launch liquid oxygen and liquid methane and transfer it into that system. The last one goes up and docks. All of the fuel gets transferred into it, and they go to the moon, land vertically on the moon, and come home. The crew launch in the capsule and meet twice on the way. So really amazing system, not possible without cryogenic refueling. Gateway will be involved in Artemis 4 and subsequent missions to make it sustainable and enable extended lunar presence. But it's also to get us going towards Mars. And Mars starts with the Mars Transportation System, which could be a big nuclear system. You can't launch that. You have to build it in space. So they're used to that. So human exploration will do that, and with a nuke probably. Interesting. Mars Ascent Vehicle can't land on Mars with all its fuel. It's too heavy to survive that landing. They say that Mars has just enough atmosphere to make landing harder. It doesn't really help you much. They do use chutes on Mars, and so they can get slowed down, but there's so much variability that it's just really challenging to land on Mars. Anyway, Mars Ascent Vehicle will land without all of its fuel. We'll land something beforehand with fuel. We'll probably drive a rover over to it and refuel and fuel it on the surface of Mars. So pretty cool stuff. All right, those are the NASA reasons. There are also some other reasons. Department of Defense is very concerned about space becoming a contested regime. We're worried about our ability to defend our satellites. We have a very strong dominance in space that has for a long time been assumed to be safe, and that might not be the case anymore. So, you might want to maneuver a lot more in space than we do now. And so servicing is a big part of that. There are commercial companies that we'll talk about later, and sustainability I mentioned. I don't particularly like the $1 billion and then turn it off, or even the cheap disposable spacecraft. I think we're going to get to a point where we buy our car, we drive it halfway across the country, and we fill it with gas instead of just leaving it on the side of the road. So that's the parallel for space right now. All right, so why not servicing in assembly? So there's a chicken and egg problem. When we built Hubble, we had space shuttle, and same with International Space Station. These two vehicles were serviceable and assembled and possible because we had a servicer, and it was an 18-wheeler. It was a heck of an instrument. So we don't have shuttle anymore. So when James Webb was conceived and developed, no servicing or assembly was planned because there was no Sun-Earth L2. That's where it goes. It's way, like I said, 1 million miles. No servicer out there. So and quite honestly, no ability to envision a future where there was a robot. I talked to a lot of people that said, "Why would we make James Webb serviceable? Humans can't go there." And I said, "Well, why do you need humans? And that's what robots are for." So there was no vision for appreciating that there might be robots capable of going out there. I can't really hold it against them. It was an extremely expensive vehicle as is, but the idea of putting a $10 billion spacecraft on a rocket, if I was there, I would not have been able to watch. If I had worked, I wasn't even able to watch not having worked on it. But the risk you take by putting anything on the top of a big rocket is astronomical. So how about maybe splitting it into 3 pieces, making them simpler to make? As the cost of launches go down, that actually becomes a pretty viable risk reduction, which is interesting. I put risk with a question mark here. A lot of folks think that it's too risky to fly up and do prox ops and capture a high-value asset. Well, frankly, it's not more risky than putting it on the top of a rocket. There's no way. Okay, so chicken and egg, what do we do? So OSAM-1 coming to an orbit near you. So NASA's developing this spacecraft called OSAM-1. Until about 4 years ago, I was the technical lead for this activity. It's going to go capture the Landsat vehicle that was never made to be serviced. Chicken and egg. I don't know which one's the chicken and which one's the egg, but we're squashing them both. We're going to use this spacecraft to refuel something that was never made to be refuelable. So autonomous rendezvous, autonomous capture, telerobotic refueling and relocation. Here's the spacecraft flying up to Landsat 7. It uses a robot arm to do capture. Landsat 7 is what we call non-prepared or non-cooperative. It wasn't designed to be captured. So this robot arm has a tool that it uses after the propulsion system on the spacecraft flies us into proximity with Landsat 7. We pull out this tool. It's called a Marmon gripper tool. That ring you see is the interface of that spacecraft to the launch vehicle that launched it. So this tool is designed to reach out and grab that Marmon interface. So this is a robot arm based on the same robot arms that went to Mars. One of the interesting things to me, it's kind of sad to me, but if I asked you how many U.S.-built robots there are in space, any guesses? Wait, let me make it easier. How many U.S.-built robot arms are there in space that aren't on Mars? The answer is 0. Okay, that's a problem. Okay, so we fly up there. This is blanketing over the fill and drain valve for Landsat 7. We have a rotary tool that has to cut that blanket to expose the fill and drain valve so we can refuel this thing. We have another tool not shown that pushes it aside. This is wiring to lock these things down. The fuel in spacecraft is pretty bad stuff. We don't want people on the ground to get exposed to it, so we put these caps on over the fill and drain valves, and we wire them down so that vibration doesn't shake them loose. Then we have an adapter that comes in and takes off this first cap. Of course, if you take it off, you got to be really careful not to accidentally let it go. It'll float away. So there's another cap not shown there that has to get removed, and then we go back and get a different tool. This is a refueling tool with a hose. And so pull that tool out. It has a quick disconnect on the end that interfaces to that fill and drain valve. Spacecraft, there's probably 4 or 5 different fill and drain valve sizes. So we designed this with a quick disconnect on the end. You just change out that thing to service different spacecraft. So that screws onto that thing, and then it turns to open the valve after some leak checks and other things, and then we flow the fuel. Hydrazine. This is a hydrazine system for those of you who are familiar with spacecraft propulsion systems. If it was biprop, it'd be a lot harder. Nitrogen tetroxide is not friendly. And so that's the end of that movie. So we refuel. In the last 5 years, we added a second payload called Spider. This is another robot arm built by the folks out at Maxar, formerly the Palo Alto guys. This is assembly of a RF reflector aperture. So a large aperture that couldn't be launched in one piece gets assembled. And then there's something called MakerSat. This is going to print a 10-meter boom pultrusion. That's about all I can tell you about that. I'll have to get Brian to tell us more about other options. Okay, keep going. This is lights on testing at Goddard. So this is what you do. How do you figure out how to make this work in space? Even though you're the servicer, you don't really get a chance to put new hardware on and fix things. So we test us like crazy on the ground. So this is some testing on the ground. Robotic servicing technology is ready. This is the lab where we're doing all that. Here's a mock-up of Landsat 7. Commercial servicers are here. This is really interesting. When people ask me about how they can afford servicing if they have to build their own servicer or pay for their own servicer, my answer is always, you don't have to build your own servicer. You just pay somebody, and you basically borrow their servicer for a few months while they come and refuel your spacecraft, and then they go do their business. So commercial industry really critical in this field, and we've got to continue to encourage it. So what comes next? We talked about Hubble. We talked about Roman. We didn't about James Webb. We didn't really talk about Roman. It'll launch in 2025. This is a Hubble-class mirror, except it's much bigger field of view. I have a picture in the backup if you want to see it. And then after that, so Roman is refuelable, so that's good. We put some features on there so that it's refuelable, much more friendly than what we're doing on Landsat 7. The National Academies, thank you, Decadal Survey for Astronomy and Astrophysics in 2020 recommended that Habitable Worlds Observatory I told you about, so that'll be in the 40s, and refuelable, modular, and upgradable. So I'm really excited about this. Not excited about how far in the future it is, but I'm really excited about this. This is going back to Hubble ability to upgrade instruments, most likely robotic, and I would venture to say that some of you in the room will be building and operating that robot. Depending on how that Starship work goes, who knows, maybe some of you will be riding that Starship out there and doing this on an EVA. But for now, I'm working on the robotic aspects. And then after that, there's concepts for very large star shades that could be refueled or assembled in space, and we talked about ISAT and big assembled telescopes out there. So some other things that are of interest, not just in astrophysics. I mentioned the Space Force. They're going to make their fleet serviceable. I won't be surprised if they have a requirement soon to put refueling requirement on all of their spacecraft. We're going to be upgrading spacecraft. The commercial industry is building tugs, and we're going to do in-space testing, and maybe we'll do some Earth observation with a persistent platform where you can launch a 100-kilogram instrument every now and then. Instead of replacing the whole platform, you just bring up a new instrument whenever you want. And then who knows where we go after that. Big things, right? Think big. Do good and great things, right? Yeah, good and great things. Let's start building, and I'm really looking forward to what you guys build in space. I can't wait to see it. Thank you. Yeah, I think we have time for some.
Two microphones.
Okay, yeah, here's one of them. Okay, and thanks to whoever put the water up here. Well done. Any
Does
questions?
anyone have any questions?
I was telling Brian that I've never given a talk to high school students that I didn't get asked about whether ET is real, so whether there's aliens out there. So
If they raise their hand, the microphone will come to them and we'll alternate.
If you raise your hand, this is for the students now. You raise your hand, a microphone will approach you, and you can then ask the question, okay?
there's one over here,
Right there.
right behind you.
Wait, you gotta go one at a time.
Hello. Does this work? Okay. My name is Valerie. I'm a junior at Cabrillo High School. And my question is, when refueling, are the machines coded to know what to do, or is it a human controlling it?
Well, so in the case of Landsat 7, that machine was built 25 years ago, launched 25 years ago. So it has no idea what we're doing to it. It's mainly a mechanical system. So what's the important things that we have to know from that is what's the, we push fuel into a pressurized tank against the pressure that's already there. And as the pressure increases, what else happens? Do you guys know? What happens with the temperature? It goes up, yeah. So we have, that spacecraft luckily already has all the things we need in it to monitor the pressure and temperature in that tank. We don't want it to get overpressurized. We don't want it to get too hot. But that data comes down through the ground operators in the Mission Operations Center. They monitor the stream from both spacecraft. They make sure that everything is going well. And they command in real time. And if we lose that link to the ground, we stop. We stop flowing. In the future, though, we certainly will build spacecraft that can do that automation, can automate that process and monitor it in real time. And in space, usually when spacecraft are having a problem, they just stop because nothing can happen to them. They safe themselves. They make sure they're in a stable attitude. And that's how we'll operate that as well. Good question.
Hello, I'm Jacob Cervantes from Simile Academy. I'm a senior. What would you consider to be the biggest accomplishment in space machinery?
The biggest accomplishment is obviously Space Station. It's the biggest thing that we've built. I mean, I'm partial to the James Webb. I think biggest in terms of complexity and performance is that James Webb Space Telescope. The mirrors on that thing, if the mirror was the size of the United States, this is how precisely formed they are. If the mirror was the size of the United States, the bumps on it would be less than 10 centimeters. So that is ridiculously hard. And that thing operates at cryogenic temperatures too, which is just phenomenal. So yeah, I think that's my answer. You guys want to pick or you want me to?
My name is Enrique. I am a sophomore for Cabrillo High School. And my question is, how long does it take to ensure the strong and resilient space capabilities of the spacecraft?
How long does it take
To ensure the, how strong and resilient the space capabilities are of the spacecrafts?
Yeah, so, I mean, how do we assure that a spacecraft is going to work? Yeah, so, if we're building something we've built before, from napkin to launch, the best we can do is about 3 years. That's going down as we start to build more small spacecraft. But these big ones, say 5 to 10 years, if the money comes at the right rate. But of course, you get about half of that is design, a little more than half of that is design. And then at the halfway point, you start integrating all of the flight systems together. And usually we do environmental testing on them over the course of a year or more. And that's where we're assuring that what we built works, that we built the right thing and that it works, right? And so we put it in through all kinds of very challenging tests. We put it in a vibration test that simulates the vibration loads from launch, which is a really not pleasant environment. We're talking 10 Gs and thousands of Gs of shock events and difficult thermal and vacuum, which, by the way, if you have to assemble that James Webb, part of why it was so hard is because not only did it have to deploy to that ridiculously flat and precise performance, but it had to survive launch. So how about this? Let's put it in some styrofoam, not really styrofoam, put the mirrors in some styrofoam, launch them to space, put them together, then they don't have to survive launch. How much simpler does that make them? So maybe in the future the answer will be a lot less and a lot less challenging, but I think that's about, that answer your question? Great.
Hello, my name is Etienne Lopez. I'm senior at Samueli. So you've mentioned that you've spent decades on designs. So here at Samueli, we have experienced what it's like to go from a preliminary design review to a complete design review. So my question is, when did you guys just call it off, say that we're perfectly fine with this design and we want to move forward with whatever is remaining?
Yeah, that's a good question. The answer is not early enough, usually. CDR, the critical design is usually we're really, really, I don't know what's a proper word to use. we're really defensive of making sure we did it perfectly. But I can also tell you in my experience, once CDR is over, once the critical design phase is over and we start building, a lot changes because we start figuring out what we didn't think of. So there's a fine balance between thinking ahead, and you got to think ahead, and you got to do all the analysis that proves it's going to work. But then once you start building it, you got to be flexible and start making those updates. So CDR is kind of about the halfway point. PDR to CDR for us, a year is pretty fast. So it's usually a few years depending on the size of scale of the project.
I'm Walter Sevilla from Samueli Academy. I'm a freshman. And would manufacturing or assembly in space cause trash to be produced?
Well, certainly everything you produce in space would need to factor that in. Yes, when we're doing servicing, we often, with the astronauts on space station and Hubble, for example, they have tether loops that they can connect tethers to the things that are holding in case they let them go because they'll fly away, and that's the end of it. So there is a concern about that, and it's something we have to factor in the design. Of course, we can't always prevent it. So there are definitely examples, oops moments where we lost things in space, and so certainly we've got to make sure that what we're building is worth that. Right? We're doing good and great things. Not putting excess risk out there. Got one down here. Oh.
Last question.
My name is Carl Benjamin Bergato, a senior at Cabrillo High School, and this is kind of a lingering question of mine, which is the rapid development of AI today. And I just wanted to ask if there's any applications for AI to be used in assisting these operations in conducting in-space assembly.
Yes, absolutely. So, AI is a really broad term. The most obvious one is computer vision. If you want a robot to operate or if you want to do a autonomous capture with or without humans on board, you have to have computer vision to enable that system. I have to know where I'm going, and that computer vision tells me. There's a lot of other machine learning things that people are talking about. One of the most interesting to me is robot control. So a robot is 7 degree of freedom robot arm, 7 degrees of freedom is like your arm, and you have a pretty amazing machine learning processor between your ears that enables you to control that arm. We can do it with software that's not based on artificial intelligence and machine learning, but we are starting to find that there are some really good applications. But the autonomy won't ever do the work for you. You have to understand the basic principles, and then you have to tailor that autonomous system to do exactly what you want. And I can't stress that enough. So learn your basic principles, tinker. Don't forget that engineering is hard not just because of the math and science, but because of the communication skills and the interpersonal skills and the cultural struggles that you go through. I'll tell you, I'm a really good math and scientist. That's the easy part, okay? And we need all of those skills. So culture them all and build your network, and people matter more than anything else.
Thank you
Okay.
very much. Thank you, Bo. That's good. That's good.